Chuck.
Hey.
So, Chuck, how do you know how big something is?
Yeah, measure it.
You measure it, right? So you pull out a ruler. Let's say it's a table, and you measure it. Okay. So there are two things working against you on that.
Mm-hmm.
One of them is, how close together are the hash lines on the ruler,
Right.
right? Because if your table ends up between two of them, then you don't know how long your table is. If you're going to report to me, you can only say it's between here and there, and venture a guess to where it is from one marker to the next.
Okay.
It's kind of like half, maybe. What you'll give me a guess, fine, but you won't know exactly because you don't have the metrics to determine that. Okay?
Right.
Now
It's like
watch.
measuring in hands. He's 7 hands tall. Really? That's all?
Well, hands is actually a specific measurement. I mean, I think the hand is 4 inches.
Oh, really?
The width of your hand. Yeah.
Look at that. I see. Now I just learned something there.
Horse heights are measured in hands.
In hands, right. I knew that the horses were measured in hands, but I didn't know that the hand had an actual unit.
It's around 4 inches. Don't quote
okay.
me on that. But
All
yeah,
right, that's
yeah,
cool.
yeah. Okay,
That's cool.
okay.
Good stuff.
Okay. So even if you had the precision to measure the length of the table, if you go down under a microscope, like a really good microscope, like an electron microscope, that's the kind of microscopes where you see all of the hairs on the bugs, and you see the eyeballs of the fly. Those kind of microscopes. If you do that, you'll see that the edge of the table is not smooth. It's actually got texture. So which feature of the texture are you going to measure it to and then report back to me the width of the table?
Well, okay.
What happens is at some point you just give up and say, Neil,
I can't.
you're
You
annoying
can't measure
me.
anything. Right.
you can't measure anything unless you
can't
just
measure anything.
agree. You just agree how you're going to take the measurement, and then you're good with that. Well, if you have that problem with solid objects, imagine the challenge measuring the extent of gaseous objects. Just imagine that. Okay.
Yes. I believe you measure that and how bad it smells.
Not all gas came out of your rear end, okay, in this world. Just saying. So you can ask, how high up does the atmosphere go? Well, so you ascend and you say, is there a sign that says you are now leaving Earth's atmosphere? No. No. The atmosphere gets continually thinner.
Right.
And you know this because as you ascend a mountain, the air pressure drops. It's harder for you to breathe. You can still breathe, but just every lung's worth of air has less oxygen in it. Mm-hmm. Okay? That's your evidence that the air pressure is getting lower and lower and lower.
Should have never smoked, man.
Okay.
God, this is killing me.
This continues. You go into an airplane. Airplanes are pressurized.
Right.
Which means they put air in there. Otherwise, you would suffocate if you roll down the windows. All right. So those oxygen masks, those are there in case the airplane loses pressure, and you're breathing very low density air, has hardly any oxygen in it. Right. So you got to breathe through the mask. That's all. Okay. By the way, you could hold your breath until you did this. I mean, this is not. You're not going to die immediately. You have to fight for them. It's just air. Okay.
Right.
You've held breath holding contests for longer than the time it'll take you to reach for one of these yellow masks.
Little cups, right? And remember,
okay.
people, always put your own mask on first before you try to put the mask on that of a child. So, which, by the way, no one had to tell me. Okay. Like when I heard that, I was just like, and what else would I have done? Okay.
Chuck was first out of the box on that one.
Exactly.
Yeah.
I was like, this kid ain't bringing nothing to the table. Really? I might just let the kid pass out just so I can get some rest.
Oh, that was the noisy kid. Right. You're not giving him the oxygen.
Exactly. Wait, let's not be so quick there, Mom. That kid is looking real peaceful right now.
Damn, Chuck.
All right.
That's cold. All right. Oh, by the way, it's also literally cold as you leave Earth's surface because you're farther away from the heat point of the heat generating point, which is Well, that's another. Scratch that. That's
Whole
another
nother explainer.
Whole nother. Okay. So as you ascend, the air just simply gets thinner and thinner and thinner.
Okay.
There is no spot where you say it ends here and it's space. No, there isn't. So you just have to agree on what that altitude will be. Pick a thing, and then just, you good with that? I'm good with that. Fine. Put it in the books. Move on to the next problem. Okay.
Okay.
So there's a guy in the 1960s named Kármán.
All right.
Okay? He was a Hungarian, I think, but worked in the United States. And he said there must be an altitude above which the atmosphere is no longer scattering sunlight above your head so that it's no longer sky blue. The blue goes away, and then you just see stars in broad daylight.
Oh, wow.
That's an interesting threshold, right?
That is.
And that's fair. There'll still be air molecules there, just not enough to scatter, because that's how you get a blue sky. It scatters the blue of sunlight, and now the sky is glowing and you can't see the night sky. You can't see stars in the daytime sky. Gotcha. So, because it's daytime. However, if you ascend high enough in the atmosphere, there's a point where there aren't many molecules above you. Bada bing, the sun is still there, but you can see stars in addition to our own star in the sky. So that's called the Kármán line. And ever since the early 60s, the Kármán line has been the functional definition of a transition into space, whether or not you were in Earth orbit.
Interesting.
Our first astronaut, Alan Shepard, went up in 1961. He went into suborbital, was fished out of the Atlantic, okay, and he went high enough to go above the Kármán line. So that counted, and so that's sort of our astronaut threshold. Kármán himself, however, knew that the atmosphere is not some rigid thing, it's gas.
Right.
And sometimes it heats up, sometimes it cools down, so it will expand, it will shrink. And so the Kármán line is not itself a definite thing. But if you're going to look for it, you'd find it anywhere between 80, 85, and 100 kilometers. Okay, that would convert to 53 to 62 miles up. Somewhere in there. Okay, and so to say, did you hit this exact point or not? That's like arguing, which edge of the table are you using to give me the length of the table? Except worse because it's gas.
Right.
So, point is, the atmosphere continues out for thousands of miles.
Oh no.
Yeah, in fact,
wow.
The International Space Station, which is 250 miles up.
Right.
How much higher than the 62-mile Kármán line is? It's 4 times higher than the Kármán line. The International Space Station is huge. It's like the size of a football field moving through the air. There's enough atmospheric molecules up there to hit the solar panels and the physical body to drop it to lower orbits than you had originally intended. So every now and then, the space station has to boost itself up back to its original target orbit because of the air molecules that hit it.
That's insane.
Yes. And that's 250 miles up. So there is no edge. And if you're going to ask me, what is the diameter of the sun? You could look this up in a book. You could look this up. The diameter of the sun, it'll give it to you. And you say, well, wait a minute. The sun is made of gas. So how precisely are you measuring that? You take a ruler and do that? Not only that, you can say, in what wavelength of light did you measure the diameter of the sun? Do you know different wavelengths of light emanate from different locations within the depth of the sun? If you're like Geordi on Star Trek Next Generations, and you look at the sun in ultraviolet light, it has a different dimension from what it has if you look at it in visible light and if you look at it in infrared light. Then if you look at it in X-rays, all different dimensions. In fact, The solar corona, the thing that's glowing outside of the moon when you see a total solar eclipse, that's called the corona, which is Latin for crown, so sensibly, right? So if you looked at that with X-rays, that's the size of the sun. Forget the down on the sun's surface, gaseous surface. X-rays, the corona is ablaze with light. And you're going to say the sun is huge. So I just want to put it out there that the dimensions of things is really just something you just have to agree to in advance. And then you all agree, you put it in the book, and then you move on. So the diameter of the sun is the diameter it shows to us using yellow light, which is right in the middle of the visible spectrum. That's the number you're going to read in the book. But they don't tell you that, but I'm telling you that.
I'm glad you did, because it's good to know they've been lying to me all this time.
Oh, by the way, and you can think of other definitions of space. I got one for you. You ready? So airplanes use fuel. It's called aviation fuel. There's a word for it. I forgot what. But anyway, it uses fuel. So fuel, our common understanding of fuel is you burn it and then you get energy. But what does it mean to burn it? It means it gets attached to the oxygen molecule, creates a third other product, right? There's that molecule, the oxygen molecule. They merge and make this other molecule, and it's exothermic. Energy gets generated. Okay. That's how cars work. That's how airplanes work. But where's it getting its oxygen from? The atmosphere. Okay? Wait a minute. But if you're a rocket and you're going to where there is no oxygen, where there's not much oxygen, you got to bring your own oxidizer. You can't depend on the atmosphere. So you could say you enter space at an altitude where an airplane can't get enough oxygen to fly anymore. And it just drops out of the sky. That's an interesting threshold. You could have done it that way. Because above that, you need a rocket. And we all know rockets equal space. Okay?
There you go.
I can think of 10 other ways you might define it. But I'm just saying, just numbers and measurements of things they're not written in tablets. You have to agree on what it is you're trying to measure, write down that number, and then move on.
There you go. Measurements not written in tablets, only commandments.
All right, that's all we got time for.
All right.
Yeah, that's a crazy subject, but I have to put it out there.
No, that's very cool.
And when you hear people arguing over the Kármán line, just sit back and chuckle and say, the Kármán line is an idea more than is an actual place within Earth's atmosphere.
Well, if I ever get into an argument about the Kármán line, my answer will be, so how big is the sun?
And also the 100-kilometer Kármán line, did you really think the atmosphere is layered into evenly divisible numbers in kilometers? Did you really think that's the case? If you look up Kármán line, it's 100 kilometers. Yeah, right. The Earth is like tight with the metric people, right? It's like, no, 100 is well above whatever Kármán was talking about. But if you want to round it up, you round it up to 100 kilometers, and that's the definition. Fine, okay? And the American definition is lower than that. We're like at 85 kilometers up. We have a lower definition than Europe and the rest of the world do.
Oh, well, yeah, that's because, we want to be able to say we went to space.
We want to be able to say that Alan Shepard went into space.
Went to space.
Correct.
Exactly.
Right.
We're the first people to do it,
Right.
It's just like we put a spire on top of the Freedom Tower, and it's like now the tallest building in the country.
Exactly.
Yeah. That's
all right, dude.
All right, man. Good stuff.
Dark Talk. Explainer. Stuff you thought you knew. Always good to have you, Chuck. Neil deGrasse Tyson here. Keep looking up.